Welcome everyone. So last unit we learned about the diode and we found out that the diode can be considered as a voltage control switch. So that means when the diode is forward biased, a current is flowing, a current flows from P side to N side. But when the diode is reverse biased, a very negligible amount of current is flowing, which we can ignore. And therefore, since we can ignore, so we can say when the diode is forward biased, a current is flowing from P side to N side. When the diode is reverse biased, no current is flowing. So when the diode is forward biased, the diode is on. When the diode is reverse biased, the diode is off. So this way, that can be considered as a voltage control switch. So that also tells us about the characteristics of a diode, which says that diode is a device that allows current to flow only in one direction. So that means the diode current always flows from P side to N side. So while in the opposite direction, no current is flowing. So diode is a device that allows the current to flow only in one direction. So if you want to compare the characteristics of the behavior of the diode with the resistor, the resistor is a bidirectional device. So that means in a resistor you can make the current flow in either direction, so depending on the polarity of the voltage. Right? Now we are going to determine the characteristics of the diode much more organized way, so which we call IV characteristics. So let's say IV characteristics means the relationship between the current that flows through the device and the corresponding voltage across the device. Let's explain these things with this simple example. Let's say we have a device which is quite unknown, which is inside the box. We call it device X. We have no idea what types of device it is. And we want to find out the relationship between the current that flows through this device and the corresponding voltage Vx across the device. For that, we run this experiment. In this experiment, we use a DC voltage source, variable voltage source, to power up the device. And every time we change the voltage, for example, we change the voltage from 0 volt to 10 volt with 1 volt increment, we measure the current. Also, we measure the voltage. For example, when the input voltage is 0 volt, we measure the current, we found out 0 milliampere, and also we found out the voltage is 0 volt. So this way, let's say when we apply 1 volt, we found the current to be 1 milliampere. So let's say we found the voltage to 1 volt. So this way, we go up to 10 volt. When it is 10 volt, we got 10 milliampere, we get 10 volt across the device. Now that we obtained around 10 points, so let's plot it. So in order to plot it, we have our graph where the vertical axis or the y-axis is the current Ix, it is in milliampere, and the horizontal axis or the x-axis is our voltage. So if you put all the values, all the points, we will find that we notice a pattern. Okay, so if you connect all the points, it gives us a straight line. So this straight line tells us if we select any point on this straight line, just select any point, this point we can obtain the current corresponding to this point, which is roughly this value, and the voltage corresponding to this point. That means this straight lines tells us about the current that flows through this mysterious device and the voltage across this mysterious device at that point. So that gives us the relationship. We know how are they related, how current and the voltage are related. Incidentally, we found out the relationship is a straight line. And we can say that the current is proportional to the voltage. Again, since it is linearly proportional, so I can say Ix is equal to M Bx, which is M is our slope, It's a straight line equation. And then M is equal to Vx over Ix, which is voltage divided by current. That gives us a resistance. So we can say that it is nothing but a resistor. So that gives us a characteristics of a resistor. So just to show you how to obtain the relationship between the current that flows through a device and the corresponding voltage across the device. So this way we should remember one thing. If you notice there is any script in any IV characteristics, if you ever come across, if you notice any straight line portion, immediately you can conclude that there must be a resistance lodged inside this device at the time. For example, we go for an hypothetical IV characteristics. Let's say it could be anything like that. And then in that, among other things, there is a portion where it looks like a straight line. So it means that at least for this region, between this region to this region, you can treat the device as a resistor. So that means any straight line, if you ever come across, always consider it as if there is a resistor. So now that we have the understanding as to how we can determine the IV characteristics for any device, so we are going to apply this knowledge to determine the IV characteristics for a diode. So for that, we go for another experiment, which is again a simple experiment where we have a variable voltage and there is a resistor in series, which is essentially a current limiting resistor, and there is a diode in series. So the variable voltage is going to vary from minus 10 volt to, let's say, up to 2 volt. So that means we are applying a negative voltage as well as some positive voltage. So we're going to get a wide range of voltage. So every time we apply any voltage, what we're going to do, we're going to measure the current that flows through the diode, and also we're going to measure the voltage across the diode for that particular voltage. And then we're going to, as before, we're going to plot the curve. In that curve, again, the vertical axis ID is our current axis in milliampere, and the horizontal axis is our voltage. Now, the vertical axis upward directions, that means positive y direction, it indicates the current is flowing from P side to N side. And the negative y direction or negative current direction indicates the current is flowing from N side to P side. And then if the horizontal axis or the x-axis, if the positive value of x-axis or positive value of voltage indicates that is forward biased, and the negative value of the voltage indicates it is reverse biased. So next, let's say we're going to apply the voltage. We start with from minus 10 volt. So when we apply minus 10 volt, so it means it looks like that, or polarity changes. So we have 10 volt, minus 10 volts. So you see the polarity changes. It's a negative terminal, positive terminal, and the resistor. So in that case, you notice the P side of the diode is connected to the negative terminal and the N side of the diode is connected to the positive terminal. We already know this is a reverse bias situation, which means the diode is open circuit, and that means the current is 0. So let's say we got 1 point. If the current is 0, so we got one current is 0, and at the open circuit condition, we're going to get minus 10 volt. So we got 1 point. And similarly, for minus 5 volt, let's say we got another point when still the diode is reverse biased, current is 0. And then for 0 voltage, this is our point. When the current is 0, voltage is also 0. So next we apply 0.1 volt, which means we reverse the polarity. For example, if I draw it here, it looks like this. So 0.1 volt. Now clearly, P side is connected to the positive terminal and the N side is connected to the negative terminal. So clearly the diode appears to be forward biased. So however, the value of the voltage that has been applied is not that high. It's very small. So this voltage is not enough to make the depletion region width smaller, because we know that when it is forward biased, the external voltage tries to reduce the depletion region width. But since the voltage is quite small, the amount of reduction in the depletion region is not that much. So therefore, the current that is flowing is very insignificant. We can consider the current is zero. No current is flowing. So we got zero current. So zero current, and the voltage will remain 0.1 volt. And then let's say if we apply 0.2 volt, we get no current as well. And then if we apply 0.3 volt, 0.4 volt, we will find that although we are applying forward bias voltage, since the amount of the voltage is not that high, it cannot cause any flow of current. And that is going to go on until we go for a voltage, let's say 0.5 volt. So at 0.5 volt, we can say the depletion region width becomes significantly thinner, so that a little bit of current starts to flow. And let's say if you increase a little bit more voltage, we're going to see an increase in current. And then if we reach a voltage somewhere between, let's say 0.6 to 0.7, we find this amount of voltage. For this amount of voltage, the depletion region thickness will become almost zero. Now we already learned that if the depletion region thickness become almost zero, which means there is no barrier remaining for the electron and hole to diffuse across the depletion region. So that means there is no barrier. So no electric field, since the depletion region thickness becomes zero, the electric field strength becomes zero. So it's not preventing any further diffusion of electron and hole across the junction. So that means after that, the current shoots up. So current suddenly increases. So now if you go even higher in voltage, let's say 2 volts, in that case, it's not going to do any effect to the depletion region width because it has already become zero. So only thing it can do is that it's going to pump in huge amount of electron and hole from external source, so that we have got huge amount of current. So we got a straight line afterward. Now this is the IV characteristics for diode. So this is the relationship between the current that flows through the diode and the corresponding voltage across the diode. For example, if I select one point here, so in that case, from that point, we get one value of voltage corresponding to this point, and the corresponding to this point, we get another current. So each point on the curve gives us the value of the voltage and current. Now clearly, we have a current when the diode is forward biased, at least after it reaches a certain value, which is the VT threshold voltage. But when it's reverse biased, we see there is no current. So that is consistent with what we already learned. Interestingly, one thing you notice, there is another region where there is a sudden step in the IV characteristics current. So any point on that part, so let's say selected for point, there is a value of current. Okay. And the current, since it is negative Y direction, the current is, and that corresponding to that point is always N side to P side. So that is inconsistent with what we said about the current through diode. We already said this current through diode is flowing from P side to N side, and from N side to P side there is no current. So that is inconsistent. But our previous statement, it is valid around this region. When it comes to this region, which we call the breakdown region, it behaves differently. So in normal reverse bias region, the current is 0 when it is reverse bias, and when the diode is forward bias, there is current. But when in breakdown region, when the diode enters into breakdown region, and the diode enters into breakdown region when the reverse bias voltage is above certain value, which is Vz. So in that case, diode enters into the breakdown region. When the diode enters into the breakdown region, a current starts to flow, and in that case, the current always flows from N side to P side. And also you notice, although at different point you might get different value of the current, but the voltage across the diode remain almost at Vz. So you're going to get a fixed voltage across the diode when it is in breakdown regions. We're going to learn about the breakdown region in detail when we are going to discuss Zener diode.